Hi, how are you? Okay, good. So, uh, today we are going to start the new chapter. Chapter 2 is about nothing but about. I briefly mentioned about what's like chapter 2, the content. It's mainly because the only purpose is to introduce you the four major different macromolecules that constitute life, like namely carbohydrates, lipids, proteins, and nucleic acid. That's all. Without knowing the different characteristic, chemical, physical properties of each different macromolecules, it is difficult to understand the following chapters about how cells are organized, how they function, and also how genes actually operate and functions, because it's all about their distinct typical characteristics are coming from their chemical nature. So it is trivial thing, and to some of you, these already you have covered in your high school biology class, and fortunately to others, some of you, you didn't have to worry about those silly, stupid information. That's good. So to put everyone on the same page, I'm just kind of try to briefly go over this, but each of this detailed information wise, I don't personally consider that as very important information. As long as you kind of understand what those four different macromolecules, their respective chemical properties are, so that you can have a better feeling about understanding the following: the cells, more important, cells and genes, structure and functions. That will be all right. In other words, I'm not going to heavily and try to focus on those any information in testing their information on the exam, because of that, the philosophy of my personal philosophy reflects on this. Although there are some of the points that still I consider that's kind of important. That's I'm going to stress while I'm going over this. And another thing is, because of that, let's see. Let's go over briefly. Hopefully, most of you, what's going on? So here you have this two handout regarding this chapter 2, which are textbooks. But the reason why you have two different versions, chapter 2 summary, EPUB, this is for the Macintosh users. Those who use the Macintosh or iOS, you can easily click on this EPUB version, then and that file will automatically go into the MacBook program. So this is a little more advanced. By doing so, you can enjoy a little better graphics and etc. For those who don't have those Macintosh or for those who are Windows users, then you do have this regular PDF version. But I try to incorporate some of the movies in the PDF version, because original textbook, to those who have the Macintosh computer have already noticed that actually our original textbook has a really beautiful, elegant graphics and animations, which those who don't have any Macintosh cannot enjoy. So as much as possible, I try to add on those poor souls who are not a Macintosh users. So that's the two differences. Okay. But this particular Yes. This chapter 2 summaries are something that is not a regular thing. Like I said, this semester, I'm not going to provide any lecture handout material, but only I'm going to provide these lecture slide versions because mainly your textbook will be your primary reference sources. But this chapter 2 is because of this little bit of a special position. This is not really something that we need to learn. But in order to go forward, this kind of basic fundamental information is necessary. That's why I provided some extra handout. That's the only thing. So don't expect that you would have another regular lecture handout version in the following chapter. This is only some of the special occasions, okay? Any question on that? No? Okay. So I will log out. Now let's go back. So this whole theme is life, on belief that life is nothing but chemistry. No matter how much fantasy you are actually putting in the life's mystery, but it is simply just nothing but a chemistry. It's all addition of these different chemicals, and somehow some magic occurred. So all those non-living chemicals gathered together and then established some very mysterious, wonderful structure we called cell, and from then on, life began. So there's a distinction between living thing and non-living thing, but actually it's very difficult to draw clear line because all of a sudden you get some of the non-living chemicals put together and then all of a sudden it became living cell. So that's it. Although no matter how much we want to deny it, but that is the truth. So this is our ultimate goal of the chapter, to understand, because these so-called macromolecules are the ones that make up all of these lives, including the different cell structures inside of the cell, which is very important. That gene, our gene, is also nothing but a type of macromolecules. So, in order to understand better how they work, what can you do? You can only study their chemical properties and physical properties. That's it. So, although this is not our cell, but simply a plant cell, but to give you a little bit of extra material, that plant cell has some extra feature of a cell wall, external barrier, in addition to our regular cell membrane, which if I draw cell membrane, it resides inside of a cell wall. So unfortunately, animal cells don't have any cell wall. Cell wall is very rigid, like this kind of material. Extra protection, but animals don't have to have such extra protection because whenever we see some danger, we can only run away from it. But unfortunately, plants don't have such a luxury, so it's better for them to have extra protection, just like that. And inside, you have so many different type of things like DNA, your gene. It's one of those materials made up of nucleic acid, and inside a plant cell, you usually find something called the starch grain, which is made up of carbohydrates and blah blah. And on the cell membrane, just like an animal cell as well as a plant cell and any other cells like bacterial cell or fungi cell membranes are basically made up of some kind of a special lipid. And not only that, along with these lipids, you do have some of the proteins. Many proteins are embedded on the surface of the cell membrane. That's the kind of basic usual structure or motif. And here, ribosome is some of the very big structure, which is very critical, essential for every cell's survival, because a ribosome's function is to make protein synthesis. So without having this protein synthesis function, no cells can survive, as we can easily understand. But this ribosome itself is some kind of real mixture of different type of macromolecule, which is in this case protein, a lot of different proteins, plus some particular type of nucleic acid, RNA. Some particular types of RNAs are in there. So that's basically what they are, the ribosomes are. So if you know exactly what kind of proteins are there and what kind of RNAs make up this ribosome, then we can better understand their function, and then we can have a better control. Why we really want to learn something about how they work in the first place? What do you think? And it's humans' ego. We just want to have some control. By learning some things about it, we can have a better control, manipulate. It's a very political, and it is not really pure reason. However, anyway, so that's the main purpose. And so all these molecules, so like, funny, macromolecules, all these macromolecules began smaller units, something like atom. That is the fundamental basic small unit of all material. Of course, you can have much smaller subatomic particles, but this is not a physics class, so we don't worry about any subatomic particles. But here we can simply safely assume that atom is the smallest unit of all different material. That's it. That's the beauty of biology. We don't really have to go too much detail in chemistry and physics, which is much more difficult subject to understand. Anyway, this atom combines and assembles to have a larger unit we call the molecules. So atom becomes a molecule, and these molecules become much bigger molecule, which now we call macromolecule. And especially, look, this organic, the term organic, only can be associated with this macromolecule. The reason why? Because organic means, what's organic? Organic is carbon. Any carbon containing compound, we call it an organic molecule. The one exception for this carbon containing, but we don't consider any them as an organic molecule, is probably this. Everyone knows this chemical? Carbon dioxide, CO2. Carbon dioxide is probably the only exception. It has a carbon. No, it doesn't count. It is not an organic, but rather, what's the opposite term of the organic molecule? Inorganic, yes. Inorganic molecule is something very simple, small molecule. Why usually organic molecule is larger? Because of this carbon. Carbon has a very special ability to gather some other stuff and together, including themselves. We are going to get to see that later in this chapter. So once you have this carbon-containing molecule, by definition, that is an organic molecule, and that is the only reason why you can, through which you can achieve this status of something macro. So there is no such thing like a inorganic macromolecule. That is not possible. Inorganic molecule cannot form huge big molecule. Only carbon containing, by definition, carbon containing molecule is an organic molecule. An organic molecule is the only kind of molecule that can generate huge big molecule, which only usually found where? In living system. And actually, the origin of this terminology, organic, something, it has a something and meaningful. Organic is something referring to an organism. So this big molecule, like organic, carbon-containing big molecule, can only be found in living material. That's why it is called the organic molecule, trying to refer the organism. Okay, so nowhere else you try to find some very big molecule containing made up of some of assemblies involving the carbons chemical bond. No, you cannot. That is the only some of the material, the living thing right nowadays, or at least some material belonged to those creatures, at least that once lived. So only the living material can show this organic macromolecule. So many different atoms arranged. We call different kinds of atom as an element. So like oxygen is an element, a kind of an element containing how many electrons, how many neutrons, and it is a kind of an atom. But oxygen is an element, but the basic structure of oxygen is a kind of an atom, made up of atom, type of distinction. That really accurate distinction we don't need to worry about. Simply put, there are so many different elements exist on Earth. Okay? And luckily, mostly we don't have to worry anything about this. This is another chemistry course, simply to show you some of the elements are synthetic, some of the elements are natural elements. That's it. So structure of an atom basically, what kind of different element, regardless of different types of element, all of the elements basic structure is made up of this fundamental same structural unit of an atom, in which in the center you do have something called nucleus, and outside of this core central area, outside at the periphery, electrons are moving around, circling around, orbiting, kind of expression we can use. If you go further, usually the number of, actually the charge, why there is a plus charge and there is a minus charge, electrons take this negative minus charge, and to compensate, to neutralize that, in the center, this we call as a proton. Proton takes a positive charge, so that usually it cancels out each other. Why? Because the number of protons and the number of electrons in a given atom usually equals. So, or electricity, the charge, becomes zero. But sometimes, not always, sometimes it can change, because here at the central core, usually you don't have any differences, change. But these electrons are always the problematic, troublemaker. Sometimes you can have one electron run away, then this charge, overall charge of the particular atom become changed. Or some other times, one atom can gain one extra electron, kind of stuff. Okay, we will get to that later. So anyway, this electron, the importance of electron is, even though the electron is, by the way, what are these gray guys here? Neutrons, yes. These neutrons they don't have any charge. However, they can contribute their weight. They are heavy. They are as heavy as these protons. So usually a weight, a kind of a mass or a weight of a given atom comes usually from all these neutrons plus protons. Otherwise, in other words, the electrons are very, very negligible, very light compound. So usually you don't really have to consider trying to figure out how heavy a given atom would that be. You don't consider their contribution from electrons. So this is something you can totally neglect. However, on the other hand, chemical property, or given chemical property of a given atom comes from electron usually. Because this is the one that circles around at the on the surface of a given atom. So one particular property, chemical or physical property of an atom usually is defined by the behavior of electron. The reason why I'm emphasizing this electron is because the chemical bond, here is the organization scheme of this whole chapter is, we first want to understand some different types of chemical bond. Why? Why do we have to know about chemical bonds? Because that is the kind of tools by which we can assemble a big molecule. So once we are familiar with, we are comfortable with different types of chemical bonds, then can we understand different types of molecules? Okay, and that's it. That is the only thing that we need to know about. And in establishing this chemical bond, electron is the only important thing. Central area of this nucleus, component of this nucleus, they don't have anything, any influence in what kind of a chemical bond on any given two different elements are going to make kind of stuff. Okay, let's go. What's going on? Yeah. So, for that matter, how many electrons are there at the very outside of a given atom is something very important. The electron number of the electron shell is the outermost electron shell, its name is called the valence electron shell. What is the electron shell? This is the electron shell. So there are some different levels of energy level of electrons they can orbiting. Okay. So the smaller the atom. What do you mean the smaller atom and then heavier atom in terms of how many protons, how many neutrons, and how many electrons that a single atom can have determines the weight of a particular atom. Smaller atom can have only a very small number of electrons. Then all those electrons can be accommodated in one single electron orbit. So this has only one single electron shell. Okay. However, bigger atom, just like a neon over here, they cannot house all their electrons in one shell. Each different shells are like paths of an electron can move around. Okay. In terms of this quantum physics, this is not really an accurate description, but we don't want to go into the quantum physics. So this is the very classical old physical concept. This is by the different energy level, electrons can move at the different levels of electron shell. So that's the electron shell. One electron shell, another level. So at each different electron shell, you have only so many numbers, some limited number of electrons you can put in. So that in the lowest energy level of electron shell, you can have only 2 electrons. So once you have exceeded those maximum number of electrons, then any other extra electrons you have to put some other next level of this electron shell, and so forth. So as a given atom big and bigger, then the number of electron shells will be increased. But however, what's important, the only thing that we need to know in this classroom is the very outside electron shell is the only thing that matters for our own purpose. So how many electron shells at the very outside? Because the very outside electron shell we call it as a valence electron shell. And how many of them are actually there determines the chemical property of a given atom in terms of what kind of a chemical bond am I willing to form. That chemical property that I am talking about here. So that's the only thing that we need to worry about. Why? Because there are certain number maximum. Let's say here the third level, this electron shell has a maximum level of electron they can house is 8. And what's the significance of this maximum number of electrons at their very outermost electron shell is stability. So for example, this neon is very noble, stable element because it filled all of these electrons at its outermost electron shell, which is 8. So it doesn't want to get involved in any kind of a chemical reaction because I don't have to, because I filled my all requirement fulfillment of these electrons. So why do I have to bother myself to get involved in any such a silly business of a chemical formation, a bond formation? So those are very lucky ones. However, not everybody is so lucky in that some of the elements like carbon, nitrogen, and phosphorus, neon, they usually don't want to because it already fulfilled the outermost, the valence electrons to its maximum. But some others, for example, oxygen, it also requires 8 electrons. However, it lacks 2 electrons. So it will do whatever it takes to obtain 2 additional electrons so that the oxygen itself can also reach to such a status of very stability. So oxygen doesn't have to worry about being involved in any kind of further chemical reaction. That's everybody else's ultimate goal. But those who didn't reach to their maximum electron, the valence electron, the maximum number of electrons, and they try to do everything what it takes to have such a status of filling out all the valence electron numbers. That's the reason why elements have this chemical bond. So depending on who you are, everybody has a different strategy of having their different kinds of chemical bond. That's what we are going to look at here. So before we run into the actual different types of a chemical bond, let's take a look at briefly for a moment of isotope. Because isotope is very importantly used in biology, in chemical, in medical diagnosis, and as well as something called the carbon dating. Probably you must have heard before. Determining how old a certain material is, also we utilize this isotope. So definition-wise, isotope is, it is the same element, however, the difference is their number of neutrons. In other words, they have the same, these are isotopes, so by definition, they have the same number of protons and electrons all over these different isotopes, but their neutron numbers are different, so that if they have a different number of neutrons, then they can have a different weight, because neutron can contribute to the weight of a given atom. Give you an example. C12, 13, 14. 3 major different isotopes of carbon. Here C12 means this number indicates the weight. This carbon 12, which is the most common isotope of existing on Earth, 98.9% of all carbons are actually this particular isotope of a C12 isotope. And 12 means its weight, which is coming from, it has a 6 proton and 6 neutron. Okay, so it becomes 12, the mass. Remember, I told you, electron, we can ignore the weight coming from electrons. So when we usually talk about the weight of a given atom, we only consider the weight coming from proton and neutron. So altogether, 6 and 6, 12. However, same carbon, one isotope of carbon, we call that C13, is a very rare, only 1.1%. is made up from C13, and it has one more neutron. That's why it becomes its whole mass, atomic mass, becomes 13 instead of 12. Okay. There's a 6 proton, 6 neutron, 6 proton, 7 neutrons. Another thing, C14 is more rare, like only less than 0.1% of our whole entire carbon. Well, other than actually C12, 13, 14, there are several different other carbon isotopes also exist, but they are extremely rare, so we don't want to worry about them. So these three are major isotopes regarding the carbon isotope. And as you can see, 12 is the most predominant isotope, C12. However, C14 is another very important carbon isotope, especially this C14. The reason why it has 14 in atomic mass is 2 more neutrons, but this one is unlike C13 or C12. This C14 is, we called what? Radioactive isotope. So not all isotopes are radioactive, but some isotope is radioactive isotope. Why is some isotope radioactive? Because it has a higher energy, so it is unstable. So in order to become more stable, they usually return to a little more stable form of atom, but by doing so, they have to release their energy, and that energy is detected from us as a radioactive energy, which is a high energy. That's the definition of the radioactive isotope. So this radioactive isotope emits energy. And once they do, we call such a process as a isotope decay. So radioisotope decay, but their rate of decay is not something random, but it's very systematic, accurate. So we can anticipate, we can measure, and we can anticipate how long it will take a given radioisotope decay into something else. Okay. And here, half-life, by definition, guess what? What would be the half-life of a radioisotope decay? A time it takes for a given isotope, original amount of a given isotope, to become half of them. Half of the original material, the isotope material, become decayed. By definition, it's a half-life. So this we don't really need to worry about. Some of the radioisotope is much more dangerous, so that we need some kind of concrete protection, but some others have a thinner protection, that's it. So this is one of the half-life definition originally. Probably giving you this would be much more intuitive. For example, hydrogen. In hydrogen, there are 3 major isotopes, and this is named, we call it tritium. Hydrogen usually has only 1 proton, but in this case, this hydrogen has 2 more neutrons. That's why it became hydrogen 3. So this is also radioactive isotope, tritium. So since this is a radioactive, we can talk about its half-life. And every different radioactive isotope has a different half-life, obviously. So in the case of hydrogen tritium, its half-life is 12.3 years. What do I mean by that, 12.3 years? After 12.3 years, for example, if there was a 1 gram of tritium, then after 12.3 years, 0.5 gram of this original will become helium, and another half, another 0.5 gram of original tritium will still remain as radioactive tritium. Get it? Okay. That's the half-life definition. And in the case of C14, it has a tremendous longer half-life. So its half-life is 5,730 years. In other words, if we had 1 gram of C14 radioactive carbon, and it will take 5,000 years until half of this will become non-radioactive nitrogen, and still another half still remain as a radioactive C14. So back in US, I had a lot of frequent occasion of dealing with C14 in my experiment. And I had to really be more extra careful whenever I deal with C14 because its half-life is 5,000 years. In other words, if I make some mistakes to contaminate some area, there is no way I can redo this. It will take only 5,000 to erase half of this. So you have to be really, really, really careful. And maybe that is the reason why even in this country, in South Korea, no one can have a license to, in academia, no one can have a license to deal with the C14. Okay. So that kind of stuff. On the other hand, this phosphorus, P32, is one of my favorite material because it has a very short half-life, so I really, really enjoyed dealing with them. So, and every Friday, usually when I was in graduate school back in US, I used to play with this P32 alone in the laboratory with the music loud played. I kind of really enjoyed in doing my experiment because I didn't really have any kind of unnecessary fear about this P32 because it will only take 2 weeks. You did something wrong, then you wait just only 2 weeks or maybe 1 month, then everything will be gone. And actually, back in the United States, even this completely decayed P32, you can even put them in the regular trash. That is not something that allowed in this country yet, but that's kind of the rational practice, of course. So here, but the point is, every different radioactive isotope has a different half-life. That's it. So S35 and uranium. Look. This uranium has 4 billion years of half-life. And it has some kind of indirect way of decaying. So instead of having some more straightforward decay product, it has after 4 billion years, in some kind of a secondary steps, it became lead, which is non-radioactive. And here, what we are going to talk about, in particular in biology, is C14 and this uranium. These two isotopes are more useful in determining the exact age of any biological specimen. So that's something that we call the radioactive isotope dating that we are going to take a look at briefly today. But in addition to that, also some other radioactive isotope we use very usefully. I mean, why would I have to deal with different radioactive isotope back in my graduate school, like a P32? In doing many different experiments, radioactive isotope has been very, very valuable tool with which we can do many different types of diagnosis and stuff like that. So basically, mainly two lines of such a utility of radioactive isotope. One is medical diagnosis, and the other one area, which is also important, is a radioactive dating. So, for example, here one in your frequent visit to a doctor's office, when you do have this like a routine diagnosis like a PET scan, and then you ingest a very small amount of radioactive isotope. In this case, this is some glucose analog. It's a similar compound similar to glucose, structurally speaking, and it is radioactive isotope, whatever, and it has such a short half-life, 2 hours half-life, so it's very safe. After ingesting, it will come out of your system, and it will only, even if it stays, its half-life is only 2 hours, so no harm will be done to. And so using this glucose, since this is a glucose analog, when glucose is required, that radioactive isotope will also go there. So for example, it is very useful to detect what area in your body some mysterious activity is going on. Like a lot of glucose is a very important nutrient. So in any area where your metabolic activities are so high, you expect that glucose will travel there, so that glucose will be broken down to provide some energy. So when energy is required, the glucose will go there. Trouble. So this particular radioactive analog of glucose we will be able to, we cannot detect where the glucose are, but these similar to glucose molecule, this radioisotope can be detected. So here, mysteriously, if you detect here, this area, there is some accumulation of this glucose analog, so we better check it out over here, because maybe some cancer is trying to be developed, is one reason why we need these things. And here, similar tech strategy, we can see a lot of this particular hot red area is where those cancers are actually being formed. We can see using this same strategy. On the other hand, in carbon dating, one of the more common isotope to use, for example, we discover some fossil, and then we want to know how old would that fossil that be. And usually one of the favorite compound we use is C14, because it has a 5,000, something like on half-life. That means probably we can estimate accurately up to something 60,000 years of those, because at each scale of a half-life, 5,000 years will be must have passed. So in other words, if you keep tracking down, then you can go up to something like a 60,000 years of accurate estimation of the age of any specimen. In the case of uranium, you can even use to estimate, test even those material up to 4 billion years old. So you can use this uranium in detecting or testing the age of some rocks, even some old rocks that must have formed in the early days of this earth. Something you can also do that. However, here one important thing is, what's the basic principle of the radioisotope dating? If I actually asked you this question, what would be your answer? If you can correctly answer this, then you can understand the principle of this radioactive dating. This carbon dating. Can you apply this carbon dating method to this living people or living any creature? Because seems like we only use those carbon dating in any discovered fossils and some of the old material, dead material, for example. But why not? Is there any, can we use this in estimating, like, lady, how old are you? You may actually answer, I'm 18. and I don't believe you, so let me check. So let me apply the carbon dating so that to see if you are really 18 or maybe something 64 years old, something. Can we do this? Theoretically? If then, why not? Why don't we do that? Because it's too dangerous, because it is a radioactive isotope, so it is dangerous for our own health, or this is like our life is too short, so it is meaningless to apply this long half-life isotope. Then if that is the case, why don't we use some isotope having much shorter half-life that's available too? The answer is no, you can't. You cannot use this radioactive isotope dating in living creature. While they are alive, you cannot. Only you can apply this once they are dead. Why is that? If you can answer that, then you understand now the rationale, principle of this radioactive dating. Anybody? Let's try it. Yes. Why not the carbon start dating while you are alive? That's exactly the correct answer, but why? Why not? Yeah, you are alive, why not the carbon inside of your system does not decay? You don't know? But that's the correct answer, yes. Only this carbon or whatever this radioactive isotope will start decay once you are dead. Well, why is that? Metabolism, exactly. Yes. While you are alive, you are constantly doing this metabolism, which is what? You are exchanging. You are exchanging all this material from outside the world. So even if you have this C14 inside, but this inside your C14 radioactive isotope will recycle, keep circulating from. So there is no way you can detect any one because that carbon C14 is not trapped inside of your system. But fortunately, you are dead. Unfortunately, you are dead. So now that C14 that somehow accidentally captured inside of your system, now there's no way it can escape because you're dead. Now it will start decay. So once you discover some dead old specimen material like a fossil, everything else will be the same because you already have some known ratio. Like I showed you, C12, you have something like 98% all over the world, same ratio. C13, you will have some like 2%. And C14, you would expect that it will be something like 0.1%, but oh, wait a minute. This has even much less than 0.1%. Depending on how old, how long you are dead, the amount of C14 inside of your system will be much, much less than your expected original ratio of C14 present in worldwide, because it has decayed and changed into something else. Nitrogen, right? So that's the rationale. That's the principle of applying this C14 carbon or any other radioactive isotope dating material. That's why, unfortunately, you cannot apply this in anybody who is still living. Okay? Okay, so chemical bond. Now we can jump right into the different types of chemical bond. Like I said, electrons are the one very important in determining what kind of chemical bonds that a certain molecule would be formed out of each. So in chemical bond, by definition, two or more elements combine together, then this is a molecule, a compound. In doing so, you have different ways, alternative ways of forming different molecules. So each individual element come together and make some kind of establishment of this like togetherness. So from now on, you and I are kind of one single same thing. Then now we call that, from then on, we call that as a molecule instead of an element. So first type of chemical bond that we are going to look at is an ionic bond. In order to understand ionic bond, we have to first understand what ions are. Ions are the element that somehow lost, accidentally or whatever, lost the original number of electrons, or somehow gained some more additional extra electrons. And then they become ions. So in other words, ions all are charged from now on. So like sodium is an element. However, sodium can become an ion, ionized to become sodium plus a positive ion, sodium. That means it has how certain sodium element can become a sodium ion in this occasion. Sodium ion can only become a positively charged ion, by the way. Once if this sodium element lose one electron, then it became out of balance, has lost one electron. So in terms of number of different protons and electrons, there's one more proton remains over here, so it will become one positively charged ion. That's how a sodium sodium can become an ion. And also chlorine can become ionized, like negatively charged ion. So when it's an element chlorine become an ionized, negatively charged ion, it can do so by after gaining one electron, extra electron, then it become a negatively charged ion. So why do they do that? Some element can easily become ion. Like here the example, sodium and chlorine. These are the very good example, of two opposite cases of to be able to become ion so easily. Why? Because I didn't bring up that actual particular diagram, so shame on me. In the case of sodium, the outside of the valence shell, the number of electrons of sodium has the outermost electron shell, there is only one single electron is there. So sodium really wants to become like a fully occupied the outermost electron shell, but because of this one single electron, it cannot do so. So if it can kick out one electron, go away, then it will become easily has a the fully filled outermost electron shell, and that's what the sodium can achieve once it became a sodium positively charged sodium ion. On the other hand, chlorine, it needs only one single electron, then it can achieve this such a the all filled outermost electron shell. So these guys two needs are actually combined together, so it can easily become sodium plus ion and sodium minus chloride minus ion. Then now they can have this some very specific chemical bond. We call it an ionic bond once they become ions. So sodium become positively charged ion because it has such a really strong tendency to do so. Once they do, it can obtain such a the most stable outermost electron shell. And in case of chlorine, the opposite. Once if chlorine obtain one electron, like ionized, then it become its outermost electron shell filled with 8 electrons. So now plus and minus, once they are ionized, then they can attract to each other. Positively charged one will always try to be attracted to the negatively charged one, and vice versa is true. So that's the chemical nature of this so-called the ionic bond. So in other words, ionic bonds are always be possible only between two oppositely charged ions. So ionic bonds are the one only we can see in the case of ions, two different ions of oppositely charged. But what can become ion easily is the kind of question. Some of the elements can be easily become ionized, and some others cannot. And in biology, we need a lot of different ions, as like in forms of a mineral. Many different minerals, so-called, are those the ionized form of the element: calcium, magnesium, and the iron, like iron, this iron. And all those different type of ions we need in the properly functioning metabolism inside of our system. So we need such ions, and different ions form an ionic bond inside of our system and stabilize their existence. And another very important usage of this ionic bond is, in this case, this diagram. This is the DNA, our DNA. Our DNA structure is basically a negatively charged material. And to stabilize this negatively charged material, we do need some very specific proteins. But those proteins have some kind of positively charged surface. So some proteins have on their surface positively charged surface, is because we do have so many different kinds of proteins. Some proteins have such a property. Okay. And then we do specifically need certain such proteins on the surface of this DNA. We will get to that later when we get to see this structure of DNA and then gene expression control tool. So these are actually another very important area we see the ionic bond is being operational. And also structure of a protein too. When we maintain some proper shape, we call the structure, protein structure, shape of protein, this ionic bond is one of the many very important factors maintaining such protein structure. So in other words, ionic bonds are very important. How strong is that? Strength is not an issue. Ionic bond is very weak. It can be easily broken. So if you are something that looking for some very reliable chemical bond so that you can depend on, then ionic bond is not such a thing. So you forget about it. However, still, even if it's chemically very weak in strength, because of these many reasons, the presence of these ionic bonds in our living system is so important. Weak bond, but very important. You will see many such examples. Not always in our living system, strong one is not always a better one. Sometimes we need a very weak one, but that's more useful things. Next example of chemical bond is covalent bond. It's something that's sharing. So this covalent bond becomes possible by sharing these two electrons from two different elements. This is a more advanced form of a concept, maybe. Sharing concept. And this is more modern you don't want to own, but you can share your cars and the materials, like so, like this. You can share anything you want to, and that's the nature of a covalent bond. Valent stands for valency electrons. Co means the co sharing their valency is what it means, the covalent bond. So why do they do that? By doing so, both parties can enjoy this such a status of maximum valence electron numbers on the outermost electron shell. So for those who can easily become ions, they don't have to worry about this kind of sharing things. Now either I can dump my one extra electron or two, then I can become easily ion, and then I can find my partner, somebody else, who can also be an ionized one, and then I can form an ionic bond. Best for their lifestyle. However, not everybody can easily be on an ion like that, like I said. Some others have a difficulty. For example, carbon. Carbon has 4 electrons at its outermost electron shell. So in order to become ion, for the sake of a carbon, either you have to dump all 4 carbons at the outermost shell or obtain some 4 electrons somewhere else. Neither of them would be easy. Dumping 1 or 2 electrons might be okay, or trying to gain some 2 electrons or so might be possible, but 4 at a time? No, impossible. That's why carbon has to rely on some other different strategy, which is in this case a sharing concept. Hey, so in the case of carbon, for example, it can have so many different partners at the same time. For like here in this case, carbon make a partnership at 4 different hydrogen at the same time. Each of hydrogen share each of these 4 electrons of carbon, so that now it establishes something like a molecule we call the CH4, which is a methane gas. Even in the hydrogen can also have this thing. Hydrogen, it is very small element, so it only takes 2 electrons for its outermost electron. Still, it needs some one extra hydrogen. So what they do is, usually they like to have this kind of a covalent bond even between themselves. By sharing 2 electrons, now it can become both of these hydrogen can enjoy now 2 electrons, which is filled in its outermost electron shell. Then now it becomes hydrogen gas, H2. Oxygen. What about this? Oxygen needs 2 electrons filled the outermost electron shell. So in this case of oxygen gas, even these 2 oxygen elements forming the covalent bond, so sharing 2 electrons together. So here 2 lines. The reason why you draw 2 solid lines is this covalent bond. There are 2 covalent bonds are formed between 2 oxygen elements, and we call this kind of a 2 covalent bond as a double bond. Single bond versus double bond. Whenever you see this solid line among different elements, then this must be a covalent bond. So by convention, we designate covalent bond in chemistry by drawing a solid line. You don't really usually see a solid line between 2 ions forming the ionic bond or some other different chemical bonds that we are going to talk about today, but only the solid lines are for this covalent bond. Why? Because covalent bonds are very strong, stable bond. So it is a strong and stable bond, and so it can be very, very useful in making this macromolecules. So whenever you want to build a huge, big macromolecule, those macromolecules should better be very stable in structure. So we rely on those covalent bond. And especially covalent bond, we invite carbon there, because carbon has an ability of what? Having 4 covalent bonds at a time. So by doing so, carbon can stretch out, expand these dimensions of covalent bond in 4 different directions. So that's how, once you get this carbon involved in covalent bond, you can expand this size of this macromolecule so big. And that's how it has been in this our living system. Okay, so that's what it something. Tetrahedra, who cares about this terminology, tetrahedra, whatever, but what it means is this. At the center carbon, this angle of this covalent bond formation is in such a way that it have a 4 equal direction of covalent bond formation. Here, you don't have to necessarily have a hydrogen, but you can have so many different things. Even you can have another carbon over there. By doing so, you can expand this whole thing to become such a huge material like this. So you can keep going on and on. So that's the nature of macromolecules. That's why all those macromolecules, you better have some carbon there. Whatever. Okay, so hydrogen bond is something very unique. Hydrogen bond is by nature, it is a kind of ionic interaction. However, it is a byproduct of covalent bond. There are 2 different kinds of covalent bond. One is a non-polar covalent bond, and another type is some kind of polar covalent bond. How are they different? Is here. These are, among here, there is only one there is only one polar covalent bond, and other 3 are all non-polar covalent bond. Can you point which one is the polar covalent bond over here? This one. Yeah, H2O. Why? The electron potential is so much different between these 2 parties. As a proper term, we call it as electronegativity, is what I say over here. This is an electron at the table listing different electronegativity over here. Oxygen, and especially in our biology system, the only 2 elements that we need to worry about, oxygen and nitrogen. These 2 guys are the 2 notorious electron greedy elements because they are high in their electronegativity. In other words, they want to take electrons from somebody else, and it has such a strong desire and power. So any other element, they have no match with oxygen. Once they get encountered with an oxygen, then they have to give up the electrons because the oxygen is so greedy and powerful. Hey, give me your electron. That's mine from now on. So whenever you have this oxygen, then you anticipate trouble because oxygen is so electronegative in terms of it is a very high in electronegativity. So this inequality creates a problem, but for example, here between these 2 oxygens, still you can maintain the balance because both parties are equally strong in its electronegativity. However, problem occurs when this type of thing happens. This poor innocent hydrogen, they sign the contract believing that from now on we are going to share our electron equally with oxygen. Then immediately they realize, wow, it was a lie. I made a mistake, because this guy, oxygen, is so electron greedy. So although on the paper they agreed to share their electrons equally, no, in reality all those electrons will stay on the oxygen side. Hydrogen, where is my electrons? No, sorry, you don't have your electrons. They are all there, oxygen side. Now, then it becomes polar, because this area will become negatively, partially although, negatively charged, whereas this area, hydrogen end, will become positively, slightly positively charged because of this unequal presence of electrons. So, although this covalent bond, ideally speaking, covalent bonds should supposedly generate the neutral, because we are sharing the thing equally. No way, in reality, those electrons are distributed unequally. So some negatively and positively charged molecules are created. Then we call that as a polar covalent bond. And whenever you have such a polar covalent bond, then each different water molecule over here, this is a water molecule, each water molecule become polar. Water is polar molecule. You have to keep worrying about this. A certain molecule would be polar or non-polar in biology, because depending on who you are, whether you are polar or non-polar, it actually determines its different chemical property and also its different activity. So you always have to consider what kind of, for example, protein in general, would that be polar or non-polar? Carbohydrate in general, are they going to be polar or non-polar type of thing? But you can easily determine. You don't have to memorize, but you can easily determine if certain macromolecule is going to be a polar or non-polar. And you better know that, because that's important to anticipate their behavior because all this system is centered around watery environment. Life began in the water, and water itself is a polar molecule because of this thing. Okay. Getting back to the hydrogen bond. So this polar water molecule is depicted here. And two water molecules, they get to be attracted each other because of this. They're supposed to be a neutral, covalently bonded molecule. However, in reality, because of this, in this hydrogen end, the white one is a hydrogen. Usually that's by convention in model building. The red one is always an oxygen, and black one is always a carbon, and the white one is always a hydrogen. But anyway, this hydrogen is this delta plus means partial charge. D plus, delta plus is positively charged, but it is not apparently charged just like ion, but very subtle charge. We call that as a partial charge, because they are not ion whatsoever, but still they have a little bit of a subtle electric charge. At this end, the hydrogen end is positively charged. Oxygen end, the other molecule, the other water molecules of oxygen will become all slightly negatively charged because of this. Then in between these two kind of very weak, subtle interaction being attracted each other. And this is what we call what? Hydrogen bond. Why? Because in making like this hydrogen bond, you always have to have hydrogen involved. But what kind of hydrogen? Any innocent poor hydrogen somehow accidentally signed up for covalent bond with other who is highly electronegative. But in reality, you can only worry about these two in biology. Either oxygen or what's the other one? Is also electronegative. Nitrogen. So hydrogen somehow having this covalent bond with oxygen, then you automatically think, oh, this poor guy is going to have the hydrogen bond with somebody else. And another occasion that you get to know is if this poor hydrogen also somehow get involved in covalent bond with nitrogen, then you also, this poor hydrogen is going to have the hydrogen bond. So either oxygen or nitrogen here, hydrogen with oxygen, then some nitrogen is over there which is also electronegative, then this hydrogen bond will be formed between these two. And same thing over here, oxygen and oxygen. So anytime you get to see this kind of a hydrogen and nitrogen or oxygen involved in covalent bond, then you automatically think, oh, there will be some hydrogen bond will be formed. And especially we are so excited about this hydrogen bond is because of this our intrinsic environment, which is watery environment. So everybody has to deal with water. And the water itself, each individual water molecule will be a center of the whole, this hydrogen bond. And because of that, individual water molecule is polar. So a lot of this molecules property, somehow have to evolve through this water's basic property. So even in this case, proteins, overall protein's shape is also determined by this kind of local areas of hydrogen bond too. So already I have mentioned two different types of a chemical bond used in maintaining protein structure. One is ionic bond, right? And the other one is hydrogen bond. Both of them are very weak bond, but very important in making up. Okay, so already so I have to stop here for a break. So after 25 minutes break, we will continue on the second part of the discussion today. Okay.